Last time we looked at the flux through a surface, the volume per unit time of a fluid flowing through a surface, for instance. That's an important quantity to be able to calculate. It has lots of other applications besides fluid flow, actually. You'll see some of them in this section. But sometimes the integrals that you get there are very hard to do. What can we do? We'd like an alternative way to do it. Just like when we have line integrals, we said, well, boy, these are hard to calculate sometimes. But in the case that the vector field is conservative, we can evaluate it using the potential theorem. And the potential at the end minus the potential at the beginning was a nice simple way. Similarly here, the divergence theorem of Gauss is going to give us a nice simple way to evaluate the flux through a surface in this special case. Suppose G is a solid with a surface sigma oriented outward, right? Where F, G, and H, the components of it, have continuous first partial derivatives on some open set containing the solid. Then the flux, F dot n ds, or physicists will just write this F dot ds with the little n assumed as part of this, is the triple integral of the divergence of f dv. Wait a minute, I'm taking a double integral and make a triple integral. It's going to make it easier. Well, it's the same thing that we had before, where we could write a line integral as a double integral by Green's theorem, and sometimes that actually did come out to be easier if it was the right shape. That's going to be the same case here. For a special shape like a rectangular box of some sort, then it's going to turn out that often the triple integral is easier to evaluate because the box just goes between constant endpoints. You don't have to break this up into 6 surfaces and evaluate the flux over each of the 6 surfaces kind of thing. So we'll have, this actually give us some advantage. But here, this is the divergence theorem of Gauss, that the double integral over a surface sigma of f dot ds is the triple integral of the divergence of f dv. So this is an alternative way to evaluate the flux. I wanted to point out just for fun, these are always interesting to read. Your book has a really nice write-up on the great Prince of Mathematics, Gauss. He's considered one of the 3 greatest mathematicians of all time, along with Newton and Archimedes. And there's this wonderful story down here that in his elementary education, he was enrolled in a school run by a man named Büttner, whose main teaching technique was thrashing, right? And he had the habit of assigning long addition problems, which unknown to his students were arithmetic progressions that he could sum up using formulas. So on the first day that Gauss entered the arithmetic class, the students were asked to sum the numbers 1 to 100, 1 plus 2 plus 3 plus 4. Oh. But no sooner had Büttner stated the problem than Gauss turned over the slate and exclaimed, in his peasant dialect, "Liget see, here it lies." For nearly an hour, Büttner glared at Gauss, who sat with folded hands while his classmates toiled away. When Büttner examined the slates at the end of the period, Gauss's slate contained a single number, 5050, the only correct solution in his class. Well, for his credit, Büttner recognized the genius of Gauss, and with the help of his assistant, brought it to the attention of Carl William Ferdinand, Duke of, it's off the bottom, but he went on to be very famous. He said, Gauss did, that he could do rudimentary arithmetic before he could speak, and all sorts of other things. So he really was a brilliant guy. He was probably the last mathematician, they say, of his time who understood all of mathematics of his day. And today we tend to just, focus on rings and fields in algebra, or classical gauge field theory, or a little section of topology or whatever. It's some little part of mathematics, and nobody understands it like Gauss did anymore. All the mathematics of the day. Well, here's use of the divergence theorem to calculate flux. I'm going to go to example 2 here. Really what I want you to get out of this section is just to realize the divergence theorem. You can write the flux integral, f dot ds, as the triple integral of the divergence of the function, and use that as an alternative to evaluate the flux. And so let's try that. Just be able to do a few problems like this. Use the divergence theorem to evaluate the flux. Suppose it's a velocity field of a fluid or something. 2xi plus 3yj plus z squared k across this unit cube. Well, there's the perfect example for converting into a solid, right? We first compute the divergence of f. Remember, it's just d dx of the first component plus d dy of the second plus d dz of the third. It's del dot for this function is the way the divergence is defined. So we take d dx of 2x plus d dy of 3y plus d dz of z squared, and we get 5 plus 2z is the divergence of this vector field. So the flux, integral f dot n ds, can be calculated. It's by Gauss's divergence theorem as the divergence f plus 2z integrated over the solid that has that surface as its boundary. So you have to have this special case that you want the flux through a closed surface that's the boundary for the solid. It's just like, you know, when you use the theorem for evaluating line integrals, you had to have actually that f was a conservative force. Similarly here, you want to have a closed surface field that you apply this with continuous first partials for the field. So we rewrite it as the triple integral over the solid that has this boundary, this surface S bounding it. And what's the solid? Well, it's really easy. X goes from 0 to 1, y goes from 0 to 1, and z goes from 0 to 1. And just we just integrate 5 plus 2z over that. And that's pretty easy, right? You just follow that through and you get the number 6. This is the flux assuming an outward unit normal, by the way. That was part of the theorem also. Let's get down to example 4 here. Suppose I want to use the divergence field theorem to evaluate the outward flux of the vector field x cubed I plus y cubed j plus z cubed k across the surface of the region that is enclosed by the hemisphere. Z equals square root a squared minus x squared minus y squared. So it's a half of a sphere. It's the top half of the sphere of radius a, right? If you square this, you can rewrite this as x squared plus y squared plus z squared equals a squared. So it's a sphere of radius a, but z being the non-negative square root makes it the top half of the sphere. And so if we want to evaluate the flux of this field through the hemisphere, we can say, well, that's the triple integral over the solid G, and it's the surface that's enclosed by the hemisphere, so the hemisphere and the plane down below it. We take this triple integral here to evaluate the flux through this surface, including the bottom of outward normal. And this becomes the triple integral. Well, to integrate over the hemisphere, we'd like to use spherical coordinates. So we replace the divergence, which if you calculate it's 3x squared plus 3y squared plus 3z squared is 3 rho squared. And in spherical coordinates, dv becomes rho squared sine phi d rho d phi d theta. When we evaluate this integral, which is now very easy because rho goes between constant values on a sphere, we just let theta go from 0 to 2 pi. Phi goes from the top down to the plane, it's 0 to pi over 2, and then rho goes from 0 to a, the radius of the sphere, and we have this triple integral, which now can be evaluated readily. You can actually pull the sine phi through here and integrate, write this as a product of 3 integrals. They didn't choose to do that in this presentation, but this integral is not too hard. It comes out to be 6 pi a to the 5th over 5. So there's the utility of the divergence theorem, and I hope that'll make some of your flux problems easier.